This is Physics 1060, Descriptive Astronomy, Lecture 16. Today we're going to talk about Chapter 18, Life in the Universe. So in this section we're going to address the questions of whether or not there is likely to be life elsewhere in the universe, and how we might discover it if it did exist. It's important to distinguish between life, which is a biochemical process, and intelligent life, which is something that we could potentially interact with. As of now, we have found no evidence of life in either form currently exists anywhere. So first let's look at UFOs. Astronomers don't take reports of UFOs seriously. Lights in the sky almost always turn out to be Venus, or weather balloons, or a military rocket launch. There's some also rare, strange atmospheric phenomena that could explain some sightings. The scientist always feels the need to go after the simplest explanation, whereas many people prefer the mystery. You are, however, much more likely to get onto TV if you say you were seduced by an alien than if you saw the lights of a police helicopter. Of course, there's also outright lies, ignorance, and deception, especially by conspiracy theorists. Reports of little green men are not taken seriously by scientists. Why would they behave the way they do? And why do they have 2 eyes, 2 ears, and a mouth? Carl Sagan once said, "Extraordinary claims require extraordinary evidence." So in other words, you have to have very good evidence before anyone will take you seriously. So what's the nature and origin of life? Well, a crucial feature of life is the ability to reproduce itself. The variety of life functions is directly related to the very large number of ways carbon atoms combine together. The information is stored in the DNA molecule, which is a code that was broken in the 1950s. Life on Earth is based on long chains of carbon molecules. So, lots of carbons, maybe nitrogen, hydrogen thrown in there with maybe some other atoms attached to them. The chemistry of carbon, which we call organic chemistry, is much richer than any other element. We have established that elements are the same elsewhere in the universe, so the laws of chemistry will be the same as well. We therefore suspect that life elsewhere will be based on carbon. But we should not discount the possibility that there's some other form of life. Silicon chemistry is very similar and is not out of the question. The important thing about carbon chemistry is that it needs an intermediate temperature range to flourish. Water also helps a great deal. We also need a source of energy to foster chemical reactions. For these reasons, we think that terrestrial planets or moons are the most likely places for life to develop. Well, how did life start? Many people dodge the question and say God did it and leave it at that. However, this only answers the philosophical question of who created the universe, not the scientific question, how did he do it? In general, the scientific approach is to see if we can come up with an explanation that does not require a large adjustment to the laws of nature. As science progresses, more and more of life's processes can be explained by chemical reactions. It is natural then to explore the possibility that life began this way as well. Experiments have been done to simulate the early conditions in the Earth's atmosphere. We're not too certain about the Earth's early conditions, but we believe that the young Earth's surface was hotter because of the increased volcanoes and increased heat from the sun. There was also a lot of lightning and a lot less oxygen. Now, chemistry experiments done by Miller and Urey in the lab used a mixture of methane, water, ammonia, heat, and electrical discharges in a flask for several weeks. After that time, they found a mixture of chemicals, including amino acids, which are the building blocks of proteins. But they did not find a self-replicating system. So this was their experiment. They had a flask of boiling water. They pumped out all the excess air to begin with. Now, as the steam came up and went into this flask, they had electrodes that had sparks that were going across it. And here we had different gases. The methane, the ammonia, the water, and the hydrogen gas. And then there was some cool water coming in and out. And so as this steam came through here, the cool water would condense it, and it would come out as water droplets. And then as it would come up, it would come back in and eventually go into the boiling water. And there was a trap here that anything heavier than water would get trapped down below. And then they looked at the liquid water in the trap at the end. Now there's disagreement about the significance of these experiments. Some people take the presence of amino acids as a sign that life might have evolved given more time, 1 billion years or so. Others say it would take an enormous step to get these simple building blocks into a sequence that can reproduce itself. Our present genetic system using DNA is very sophisticated, and we have not yet come up with a scientific theory of how it came into being. Maybe there was an earlier system that came into being more easily, which changed into the present one. If we look at the geological record, we estimate that life began on Earth in the form of very simple organisms about 3 to 4 billion years ago, when the Earth was a lot younger than it was now. Remember, we showed earlier that the Earth formed about 4.6 billion years ago. Early life was very primitive and all in the ocean. Life on land is only about 400 million years old, 1/10 of the Earth's history. Humanoid history may be only 1 to 2 million years old, civilization a few thousand years old. Our ability to think about communicating outside our planet is perhaps 50 years old, rockets and radio. The main point here is that there's been unintelligent life around for a long time, but intelligent life for a very short time. In fact, if you looked at a timeline of the Earth and compared it to a year, the formation of the Earth and origin of life maybe be around March. And we had all these different periods of different life appearing on Earth, life on land only occurring around Thanksgiving, and humans and human civilization only in the last minute or so of the year before the end of the year. So, we have just started asking the question, is Earth it? Where else could we start looking for living things? What about our solar system? Well, if we look at the planets in our solar system, there's not a lot of hope of finding life there. We looked for life on Mars starting in 1967, when a lander craft analyzed the soil for signs of life-like chemistry. There was none seen. There's been some recent evidence of fossilized life on Mars, but that would be life billions of years ago. And there's not a lot of disagreement on whether this fossilized life is actually fossilized bacteria or just some strange crystal formations. There's a lot of debate on the Mars fossils right now. Venus, of course, is another possibility, but its high temperature makes it inhospitable. Europa, the moon of Jupiter, is now considered the most likely possibility because of the liquid water under its icy surface. Everywhere else in the solar system is very unlikely to harbor life. Doesn't mean that life can't exist there, only life like ours cannot. What about the rest of the galaxy? We said that the best bet for life is on planets, but planets around other stars are very hard to find. There is some tantalizing data coming in now, but we cannot detect anything like the Earth around another star yet. But what we can do is make estimates of the number of planets that might exist in the galaxy. We do calculations of the probabilities of stars having planets, the probabilities of these planets having temperate zones, the probability of life forming, the probability of it evolving to intelligence, and the probability of it not destroying itself. An early approach to the statistical problem is known as the Drake equation, after the U.S. astronomer who pioneered the analysis. The Drake equation states N is equal to R times Fp times Ne times Fl times Fi times Fc times L. Well, what does that all mean? N is the number of civilizations in our galaxy with which communication might be possible. Our star is the average rate of star formation in our galaxy, which we said was 2 or 3 a year. F sub p is the fraction of those stars that have planets. N sub e is the average number of planets that can potentially support life per star that has planets. F sub L is the fraction of the above that actually go on to develop life at some point. Just because it can potentially support life doesn't mean it happens. F sub I is a fraction of the above that actually goes on to develop intelligent life. F sub C is a fraction of civilizations that develop a technology that releases detectable signs of their existence into space. And L is the length of time such civilizations release detectable signals into space. These are very shaky calculations, and there's a lot of disagreement among astronomers what the estimates are. Optimists estimate there could be millions of inhabited planets in the galaxy. Pessimists estimate only one, us. It turns out that the main uncertainty is how long a civilization lasts before it destroys itself. So, let's assume for a second they exist. How would we talk to them? Well, one way is space travel, but contact with another civilization by direct space travel is very unlikely. The furthest distance humans have traveled is 400,000 kilometers to the moon. The furthest distance a robotic spacecraft has gone is 4 billion kilometers to leave the solar system. It took over 10 years to get to the edge of the solar system. It's 10,000 times farther to the nearest star, 100,000 years at current technology levels to reach the next star. However, that spacecraft that's leaving the solar system, Voyager, carried messages to maybe a potential discoverer. So if we can't go there, maybe we can detect them based on the radio signals coming from them. I recommend that you watch the movie Contact. It's one of the best science fiction movies there are about maybe a first contact of an alien civilization. Electromagnetic waves are the fastest possible way of communicating, so it's far more likely that contact will be made by radio than physical travel. Of all types of electromagnetic waves, radio waves are the best for traveling through the galaxy for technical reasons. Now, although we've had radio technology for 100 years, we are already capable of sending and transmitting information between the Earth and nearby stars. Messages have been sent into space towards nearby stars in case they have habitable planets. There are modest SETI, which stands for Search for Extraterrestrial Intelligence projects by NASA using radio telescopes. In California, there's also a SETI Institute that is the focus for scientific searches for extraterrestrial life. What are we looking for? Maybe the sounds of civilization, TV, radio, etc. You could learn a lot about the Earth just by the random signals we give off. Doppler shifts could give you the periods of the year and the day. You could even make a rough map of the Earth from the location of transmitters as they move around the Earth. Or maybe definite signals that are being sent to Earth. Which brings us to something called the information bubble. Why would anyone send us signals? In the last 70 years, we have started to give out strong radio waves from the Earth, radars, TV transmissions. These signals have reached 60 light years, 70 light years into space and have passed hundreds of stars. If anyone is watching, we may have been noticed. If our signals were seen by a star 10 light years away, we could get a signal back 20 years after we sent it. So one plan is to watch the nearby stars within our information bubble. And the number of these increases each year. So, if we've been sending radio waves out for 70 years, we look at all the stars that are within 35 light years away from us to see if we're getting a signal back. If we get a message, should we answer? The problem is that if aliens do exist, they are probably very, very much more advanced than we are. Remember, the bare bones history of the Earth is life for maybe 4 billion years, civilization for 4,000 to 6,000 years. Now let's suppose there were 2 other planets where life evolved almost exactly the same way as Earth and formed at the same time. Now we're going to call Earth plus about 0.1% faster than us, and Earth minus evolved 0.1% slower than us. Earth minus would be 4 million years behind us, and Earth plus would be 4 million years ahead. We would not detect Earth minus, but Earth plus would have had civilization for 4 million years, 1,000 times longer than us. There would be no contest. If we met and had conflict, we would lose. More likely, the difference in evolution would be measured in billions of years, not millions, so the difference between them and us would be like the difference between us and a sea urchin. Some people have extended this argument to say that if aliens exist, some of them should have become so advanced they should have populated the galaxy and solved the problems of interstellar space travel. If they are so smart, why haven't they colonized the galaxy? Another idea. If God created life throughout the universe, he could have done so having all the civilizations evolve at the same time or the same rate. There could be a lot of people asking the same questions as us. Maybe they exist, and maybe they don't. Maybe we're it. What do you think?